Here to talk about search. And really the topic is why your agent can't find the right documentation and how to fix it with Postgres. My name is Jacky. I'm a dev advocate at TigerData. You might know us as Timescale DB. Previously, I worked at Pinecone, Oracle Cloud, Single Store, Looker. Been in the data space for over 10 years now. Might not look like it, but yeah, I'm kind of old. Fun fact is that I have my own AI search SaaS. So, outside of work, I still work on search, which is probably the most boring thing out there. I'm sorry, not super well-rounded. You can scan this for my socials if you want to add me on X. My tag is the same across all platforms, on Threads, on X, on LinkedIn as well. So feel free to DM me if you want to ask me things or just see what I like to type randomly. Agenda is pretty simple today. 5 simple things. Why vector-only search silently fails on documentation. What is hybrid search? Why Postgres, a database? How to set up hybrid search in 3 steps. And what is the advantage to something that we're releasing? We released last week called pgvector. What is the advantage of that? And I've made every slide super screenshotable. So if you want to just take pictures of things, go ahead. Made it so that it's really shows up pretty nicely, hopefully. We have a prize at the end. It is this Darth Vader helmet Lego. The challenge is who can make the best Darth Vader breathing noise. I'm joking. The question is actually pretty simple, which is what is the most useful thing that you can build with hybrid search? Come to me afterwards and tell me what you want to build with hybrid search, and I'll give it to the best answer. So hopefully you're paying attention during this presentation. Don't fall asleep. I like to gauge the audience a little bit before I start presentations, just to see how things are. Can I get a raise of hands of who has used search in an LLM or AI agent before? Wow, okay, so pretty much everyone. Okay, let's take a little step further. Who has built search for large language models or AI agents? Things like RAG, retrieval augmented generation, graph RAG. All right, sweet. Actually, a lot of people, so that's good to know. I think you guys are gonna learn a little bit of something today, hopefully. Before I begin on the pitch of hybrid search, we have to first talk about the most basic search out there for AI, which is vector-only search. There is, vector search is actually pretty good, I won't lie, for documentation search, but there is some problems. One problem is that it is a little too forgiving with exact terms. Who here knows what vector search is? Okay, wow, okay, so it's a pretty technical crowd. But it's okay if you don't know. Really basic vector search is, you can think of vector search as being able to find text with similar meaning by comparing their semantic mathematical representations. Sounds pretty nerdy, but it's honestly pretty simple. What that really means is it is finding similar words to other words or similar text to other texts. And vector search means an array of numbers. In the context of what we're talking about in this presentation, these are generally fixed size arrays, and they are dependent on something called vector embedding models. And each individual number within this array is generally a range of -1 to 1 or 0 to 1. This is a normalized number. And these numbers are generated by embedding models, which is basically just magic that takes input text and transforms them to these numeric representations. OpenAI has their own, Cohere has their own. There's a lot of these vector embedding models. One of the most popular ones is called the OpenAI Text Embedding 3 Small, and that has 1,536 dimensions or 1,536 numbers in this single array. And when it comes to vector search, you can see on this graph that there are some values and words on this 3D space. In a real scenario, there's going to be 1,536 dimensions as opposed to 3D, but humans can't see beyond 3D, so there is no real way to represent that in a 2D space. So in this example, let's talk about music, for example. You can see that Metallica and Slayer are quite similar to each other. So semantically, in a vector space, it is similar. It's close to each other. Meanwhile, you might have Bob Dylan. That is very far from Slayer. And same thing with Genesis, it's very far. So if anyone ever tells you what vector search is, you can think of it in a 3D space. Things that are close to each other are similar. Things that are not similar are going to be far from each other. That's a very simple representation of that. And the problem with vector search and embeddings is that they are quite forgiving with exact terms. I mean, that's kind of the point, right? Because we're trying to find the meaning of things as opposed to the keywords or the similarity of keywords. So according to a vector embedding, PostgreSQL 17 is going to be very similar to PostgreSQL 16. Similarly, max connections is going to be quite similar to connection limits, even though they mean, because they mean similarly. And Python 3.12 and Python 3.11 is going to be quite similar, even though we know that version-wise, those are actually very different, and the APIs are going to be quite different. So the problem with vector search is that semantic similarity does not mean the exact match on a word level. So this really affects the accuracy of your retrieval. And on a use case level, let's say you have a docs chatbot, right? It's going to return deprecated API methods because different versions are going to return different API methods. For a coding assistant, it's going to suggest non-existent syntax in the user's framework version. Very common problem if you use Cursor or Claude Code or any of those coding agents. For a troubleshooting bot, it's going to recommend fixes for bugs that don't exist in a current version if it has incorrect retrieval. And again, with config guides, it's going to provide incompatible settings with each user's database version. So let's switch gears a little bit. What is keyword search? Has anyone ever used or know about keyword search? Okay, again, if you've used Google, if you use basically any search bar, you've probably used keyword search. So, Google search is one good example of keyword search, where it catches the exact terms, it catches the exact version numbers, it catches the exact API names and config parameters. But it misses things that exist in semantic similarity, which is like it won't be able to catch synonyms. So the word anger is not going to be matched with fury because they're very different keyword-wise. It's not going to be able to match related concepts, paraphrasing, or context. So things that semantic search is good at is things that keyword search is not good at. I think you guys are knowing what I'm trying to get with this. Keyword search is very strict with the meaning. Connection pooling is not the same as max connections, even though they mean the same thing. Tuning database is not going to be equal to performance optimization, even though they mean the same thing. And I don't have to keep going on this. So basically, keyword search is too strict. Exact matching does not mean understanding. So what's the solution here? I think it's pretty obvious. You want to combine keyword search with semantic search, also known as hybrid search. So what if we combine these two? Vector search is very good at things like understanding concepts, synonyms, related topics, and it's aware of context. It's what we use semantic search for. Meanwhile, keyword search, the actual algorithm itself is called BM25, known as best matching 25. It is able to match exact results, and it handles versions perfectly. It deals with all the API methods that you might have in your code base or in documentation, and it is very focused on precision of the actual words itself. And then we combine it using another algorithm called RRF. That stands for reciprocal rank fusion. That sounds really fancy, but it's actually a pretty simple little equation. And I'll talk about what RRF stands for in a second, but just keep a note on this. We're combining these two technologies together using this algorithm that marries two different things together. So let's have an example. The question that I might have for documentation might be like, how do I configure max connections in Postgres 17? In a hybrid search result, it's going to bring up the exact things that I want, which is things like a title that says Postgres 17 max connections config, But in a vector-only search result, it might bring things that are semantically similar, but it is not the exact thing that I want. So it's going to bring me results like Postgres 16 connection guide, which is not correct because we're on Postgres 17. It's going to give me MySQL max connections, which again is very similar semantically, but it is MySQL, which is a completely different API than Postgres. And it might give me things like Postgres 17 new features, which is completely not what we want. So I keep mentioning Postgres. Why? Why does Postgres matter in this case? I work for a Postgres company, so it is kind of like I might be pitching Postgres, but I really do believe in this database technology. And really the point is that managing separate databases and synchronization pipelines is a nightmare. This is what a typical doc search architecture looks like. You have your documentation stored in Postgres. So these are things like texts, version numbers. They're stored in your typical Postgres database. You might have things like your user table, your authentication, information about your users itself. Then you have to build a synchronization pipeline that synchronizes the stuff in your Postgres database to your vector database. So vector databases are like Pinecone, Weaviate, Quadrant. You've probably heard of these. And then you serve the results to your app. And this is what the system looks like. Your docs lives in Postgres, and you now have to have 2 extra systems for hybrid search. Vector database for your vector search, and something like Elasticsearch for keyword search. And this is what a very simplified architecture example looks like, where you have to build your own complex ETL pipeline. And as I've said, I have my own AI SaaS search startup, so I had to build my own Postgres database, and then also had to build a custom ETL pipeline that syncs my vector database, and it is a complete nightmare. There are things like you have to make sure that when you update your Postgres, you have to then send these updates to your vector database. If you remove something from your Postgres database, you have to then synchronize it to your vector database. If one system goes down, you have to run another cleanup job to resynchronize everything. There's something called eventual consistency, where what that really means is that you have stuff in Postgres, you emit the change to vector database. There is an eventual consistency where it does eventually synchronize, but there is a small period of time where it's not synced because there's latency involved with the processing. So a ton of problems with these synchronization pipelines. It's a nightmare. I'm still trying to improve it. So what could go wrong? Your sync pipeline breaks. Something has an outage. You have to resync everything. Eventual consistency. Schema changes means that you have to update both systems. And again, more systems is like more complexity, more payment. Your CFO might get pissed at you because why did you spend $1 million on Pinecone? But Pinecone might be happy with that, but not your CFO. So Postgres, again, here to pitch Postgres. Postgres has actually had keyword search since version 8.3. And if you're not familiar with the Postgres ecosystem, 8.3 was 2005. Maybe older than some of you here. But maybe as old as some of the careers you've had here. There is a technology called TS-Vector and TS-Query, which is basically a pre-processing pipeline where it tokenizes text. What that means is it breaks sentences down into its individual words. It removes stop words, so things like presenters like me, we love saying it's going to remove those, thank you. It does stemming, which is converting words that have things like running. It might convert that to run because ing itself does not really matter in the context of keyword search. It has @@ operators, which matches documents with Boolean matching. So what that means is it only brings results back if there is a match for all keywords being searched. There's a really simple ranking algorithm called TS-Rank, which scores results by word frequency and position. And I'll talk about something really funny about this in a second. There is a GIN index, which makes Boolean matching really fast. It supports 29 languages out of the box, so it does all the pre-processing for you. The thing is, this technology is actually very mature and it's used by a lot of companies, and it's actually has really great primitives. But in the end, the ranking is poor, and after a certain scale, it doesn't perform very well. So what this really means is that Postgres needs modern ranked keyword search. If you've heard of Elasticsearch, Lucene, those use modern ranked keyword search. The problem with TS-rank, that ranking algorithm I was talking about, is that there's no weighting. It's specifically called IDF, which means inverse document frequency. So if you have a lot of words that are the same word itself, it's going to rank more highly because that the frequency of coming back is like high, right? Keyword stuffing also works. So early days of Google, you could get really good SEO by just having a blog, which is just the same words over and over and over and over again, and it ranks really high. Actually, sorry, this is probably preceding Google, maybe Yahoo, Ask Jeeves, et cetera. Anyone old enough to know what those are? There's a bias for length, so if you have a very long document with the same words, it has a bias towards that, and so as a result has really poor ranking quality. But the advantages to best matching 25 is that rare terms matter more. So I'll give you an example of what that means later. It's interested in the top 20 matches, or top K matches, typically 20. It deals with this term saturation problem where the more the word happens, the higher it ranks. It normalizes the length of the document, so a very long document that's 100 pages is about equal as a document that is 1 page long. And it's also industry standard used by Elasticsearch, Lucene, OpenSearch. So this is actually a very mature technology. And I want to show you this example here, which is this research paper, quote unquote, research paper called Chicken, 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 Chicken. And it's written by this person called Doug in the University of Washington. And he was able to get this chicken paper ranked very highly at certain publications because it's just the word chicken repeated like thousands and thousands and thousands of times. And so you can see that it is very focused on chickens. And with TS rank, it's going to rank very high because there's no IDF weighting. It's able to be keyword stuffed. But with BM25, this is actually going to be penalized because every time a common word happens more and more and more again, it's going to have a lower score in terms of ranking. So it's a really funny example that our engineer found. So we're happy to release last week, but announced here first, is PG Text Search, which is a plugin that we built for Postgres. And the beauty of Postgres is that everything is open source, and you can just install plugins for your needs on top of Postgres. So you can install PG Text Search on TigerData's Postgres implementation. It is state-of-the-art modern ranked keyword search, so things like Elasticsearch, it's similar to this. TJ is the staff engineer that built this, and he says it's a deeply unoriginal architecture, which is good in Postgres world, in database world, because that means that it is reliable and it's been tested for many, many years. It is a borrowed architecture from Lucene, Tentav, and it's used by Elasticsearch, and it has the primitives such as BM25 access method, has the eyeball ranking operator, we call that the eyeball, and it has different types that you can use such as query and vector. And so I think maybe obvious at this point what I'm getting into, which is hybrid search is the combination of PG text search with pgvector scale, which is our implementation of high performance vector search. And the beauty of Postgres is that you can combine your documents, so your raw text, with vectors using pgvector scale and with a keyword index, BM25, and it's all in Postgres. So what this means is that it simplifies your stack really well. Your CFO doesn't get angry at you. It's simple. Your engineers can thank you, and you don't have to deal with this complex ETL sync pipeline that everyone gets nightmares from. So here to show you really quickly hybrid search in 3 steps. How am I doing for time? 12 minutes? Okay, perfect. Hybrid search in 3 steps. So if you want to, I've offered 2 ways for you to save this. I have the QR code to our documentation for PG Text Search, and I also shared a little code snippet for you on how to set this up in 3 sections of SQL. So really, it's quite simple. If you're familiar with SQL, if you're familiar with Postgres, you can install extensions using the create command. So you install vector scale, which is PG vector scale, and you can install PG text search using create extension PG text search. You create your documentation table. So it's 3 columns. It has your primary key. It has the content, which is the text itself, so like your blogs, your documentation, your APIs. And we have a embedding column, which has the dimension of 1536, which is the number of dimensions used by OpenAI's text embedding small. And then we just create 2 indexes. An index in Postgres is just a very efficient lookup of certain data types. There's pretty much an index for everything available on Postgres, and so we just use the same concept here. We use the disk ANN algorithm that's developed by Microsoft, which offers really fast lookups of vectors, and we use the distance algorithm of cosine similarity. And then for BM25, we create this index for the keywords, and we're using the text configuration of English. And the reason why to specify English goes back to the pre-processing I was talking about earlier for keyword search, which is stemming, making words shorter, making them more consistent, and then tokenizing them. So got to specify your language, and this offers 29 languages. Next, we do a select of the keywords that we want to look up. We use the concept of the eyeball operator, which calculates the rank using BM25. And then the results that get returned are negative, and it's sorted by how negative it is, because the more negative it is, the better of a match. And then we use a repeat operator, which it's basically for query optimization. So this just gets you better results than TS rank. So this is what the select look like. And then we combine the two searches that we just did, the vector search and the keyword search, using RRF. And this is called hybrid search. So as you can see, you don't have to read everything. You can just listen to me talk. You get the top 20 results from your vectors. So these are the top 20 semantically similar results. And then you get the top 20 most relevant keywords. And then we use a industry-tested algorithm called RRF, reciprocal rank fusion, to combine these two results. And how RRF works is it uses a very well-established and very simple algorithm written by these three really smart people from Google and University of Waterloo. And basically how it works is it is the value of 1 divided by k plus rank, where k is 60. And this is a standard constant from the original research paper that's listed here, written in 2009. So again, this is a very well-established technology. And this value of 60 was actually derived from really constant testing, and it works well across many types of data sets and search scenarios. And this is how RF calculates how to rank the top 20. And basically, documents that rank high in both the vector and semantic searches get the highest combined score. So this means that it rises to the top. So what this really means is, just because something ranks high in vector similarity, so semantic similarity, does that mean it means that, but it ranks low in keyword search, then the results would not appear as high as results that rank high on both keyword and semantic search, because really we want the best of both worlds, right? So that's really how this RRF works. And RRF is not the only algorithm out there that lets you combine these things. There's plenty of other algorithms, but RF is simple enough where it's computationally simple. So that's why we chose it. And again, it's very mature. It's over 15, 16 years old. So let's really talk briefly about the advantage of PG text search. It really is just about better ranking and better engineering simplicity. So here's a slide that shows all of the benefits of PG text search. It offers things that TS rank, which is the more naive implementation. It offers just better counters to keyword stuffing, like that chicken research paper. So it has the IDF weighting, so rare terms like max connection is going to do better than very common terms such as database. It fights against term saturation, so repeating keywords like chicken are going to rank much lower than as opposed to TS rank. It also normalizes the length of documents, so that documents with 100 pages is going to rank similarly to documents with 1 page. And also, because it's on Postgres, it's just one system. So you just write to Postgres, and both of the indexes for keywords and semantic search and vector search are going to update atomically. There's no sync pipelines that I've explained before. Really scary stuff. There's no eventual consistency. That means that once an update is being done, it's done. There's no catch-up related. And SQL is something that we've been writing for 30, 40, 50 years. There's no need to reinvent the wheel with fancy graph rag, vector search, document databases. You can use all the really awesome primitives of Postgres, such as filter by metadata, which is very common in vector search. You can join things. You can use all the other data types available, like time series, JSON-B, geospatial. Talked to a few of you today. You mentioned geospatial. So all the Postgres primitives work, and you don't need to manage or pay for Elasticsearch, OpenSearch, Pinecone, Weaviate, Quadrant, and it basically eliminates this seriously non-trivial part of managing multiple infrastructure. It is a very painful thing to do. Do not do that. This is available now on Tiger Cloud. PG Text Search is available on preview release, but we're making constant improvements to it, so making it more up to date with the current standard. We just released this last week, but we have tons of new updates coming up. PG Vector Scale, we've been using this in production for a few years now, and it's great, very performant, and actually performance-wise, it's better than Pinecone. Which is the previous company I worked for. That's why I joined TigerData, because it felt pretty bad. Anyways, so yeah, we have a free tier. You can sign up for your free tier straight in the CLI. We just released an MCP server that makes it super easy to create a free tier account, create a new service, spin things down, do all the CRUD operations that you need to, and this is how you enable all the extensions. Our docs are available in the QR code, and if you just want to see the docs in general, this is docs.tigerdata.com. Appreciate everyone listening. It's afternoon, Friday, and if you want to follow me on socials, this is it.
Thank you so much, Jacky. Are we doing this now, or are you doing the giveaway later?
Yeah, so I can take time for a few questions, and then if you just want to swarm me afterward and tell me what you want to build with hybrid search, I want to see the most useful thing that you can build with hybrid search, and I'll give the best answer to this. I hope you guys were paying attention to what I was talking about.
Great, let's move on to questions then.
Hi, this is a great talk. Thank you so much.
Thank you.
Question for you. Does this, do your packages work with, or your extensions work with AWS RDS?
So PG Text Search does not currently work for anything other than TigerData's Postgres, but I think the intention is to open source that so you can you can use it with other Postgres solutions. PG Vector Scale, I believe, works with RDS because it is open source. And we also built Timescale DB, which is the company that we're known for, the product we're known for. And that also works, I believe, in pretty much every other Postgres vendor as well.
So maybe in the future?
Yeah.
All right, thanks so much.
No problem.
Thank you. Any more questions back there?
Thanks. This looks awesome.
Thank you.
Question for you. Let's say that I were to propose that we use this, and
yeah.
A natural question coming from our team would be, okay, how do you measure how much better this is?
Yeah. Yeah, so we, as a database company, we do evals and performance analysis on everything release. So when it comes to PG Text Search, we are still working on the benchmarks, which should be released in a month or two, because we just released this last week. But for PG Vector Scale, for time series, Timescale DB, we have benchmarks on our blog, and they show all the raw numbers. And I believe since it's open source, you can actually run it on your own infrastructure just to test it yourself. Just make sure that we're not making stuff up. But yeah, so TLDR is that everything except for PG Text Search has benchmarks available. And we will release benchmarks for PG Text Search very soon.
All right, thank you.
Yeah.
Thank you. I think we have time for perhaps one more question.
Yeah, thanks. Great talk. Yeah, so for something like RAG, where you're passing the results to an LLM,
Yes.
I guess the typical approach has been to have a broad search range and then let the LLM do the keyword search part kind of implicitly.
Yeah.
I'm wondering, and the example you showed is kind of fetching 20 results and combining them.
Yeah.
When the list is that short, can't the LLM just do a pretty good job on the keyword search itself? Or is the idea to have like a much larger list at the initial step so that?
Yeah, so your question basically is you can let the LLM decide on what the best search results are and then formulate the answer based on what it thinks is the most accurate thing? That's a really good question. So I think you've heard of something called context engineering before, which is basically you want to serve the best results to your large language model before the inference step. What that does is, one thing that large language models aren't actually very good at is determine what the right thing to choose in context-wise. That's why context engineering exists. So we serve the most accurate results before the large language model even infers based on what it knows. So the TLDR here is that we serve the best results before the LM even generates an answer, so that doesn't get confused. And I personally don't think large language models are going to get better at determining what the best results are. And so yeah, that's really, I think, the answer.